Hi everyone, my name is Aditi Srinivasan, and I'd like to welcome you to our 4th Sammamish Teen Science Cafe POV series talk. The Science POV series is aimed at bringing bright student experts in various science fields to not only talk about what they are passionate about, but also how they explore interesting avenues of science as a high schooler or as a college student. We are doing this series virtually, of course, due to the COVID-19 global pandemic, so we hope that both you and your families are safe. Today's speaker is Nathan Apfel. Nathan is actually a rising senior at Tesla STEM High School who loves theater, history, and science. He is a curriculum co-director at the Tomorrow Project, which is a national nonprofit focused on environmental education for children, and he is also very passionate on political and social issues, especially those surrounding the LGBTQ community. Nathan has been also interested in linguistics for as long as he can remember, even being a member of the Linguistics Society of America. This specific interest, along with the passion for neuroscience, led him to come up with a project exploring the scientific nature of our thoughts. So without further ado, please welcome Nathan Apfel.
Hi, I'm Nathan Apfel, a rising senior at Tesla STEM High School, and I'm here to, most simply, tell a story. The story of how I spent my time leading up to and during the first months of quarantine trying to further my involvement with the world of science. It's a little bit technical, and there are some mathematical details which you don't really need to understand, but it's a story I hope you enjoy. It's a story, I guess, about how linguistics and neuroscience meet to do something unimaginably cool. It's a story about my time with the science of mind reading.
Linguistics is one of those sciences you don't hear that much about, but I've been fascinated by one or another of its applications ever since I was a little kid. For example, in one of my earliest memories, I'm sitting on my dad's bed when I suddenly proclaimed to my younger brother that S is just Z, but in black and white. What I'd stumbled upon was a phonetic phenomenon called voicing. Z is the same shape in your mouth as S, but when you say Z, your vocal cords are vibrating. Try it. Zzz. Cool, right? At least I thought so. But as time went on, other aspects of language began to grab my attention as well.
In 9th grade, I was diagnosed with anxiety.
Thinking too much about how exactly my heart was working would send the language of my thoughts into a downward spiral so strong that I could nearly, if not completely, pass out. It was that language, that internal monologue or inner speech, that drew my strongest interest. So, because I go to Tesla STEM High School and took psychology, when I was enrolled in a regional science fair called STSCN, though anyone can sign up, I decided my project would focus on the neuroscience of that inner speech. The first step in this science fair, and the most nerve-wracking part, is finding a mentor. You need one to compete in the fair, and since my project was going to require some level of neuroimaging, I needed one that could be hands-on. I ended up emailing 30 people from universities in the area. Most didn't respond. The ones who did generally pointed me elsewhere. Finally, though, someone was interested. Dr. Christina Zhao, PhD, of the University of Washington. She would be helping me throughout this process.
There is simultaneously very much and very little known about the enigmatic target of my investigation, inner speech. Inner speech is basically the voice you hear in your head when you're thinking or reading. Some people claim not to have such a voice, but there is very little evidence to back this up, as we really can't pinpoint anything. To understand it, there are a lot of little technicalities in the neurolinguistic field of voices you can hear that we need to get out of the way. First, inner speech is different from auditory imagery, imagining you're listening to your own or someone else's voice. It activates different parts of the brain. Second, inner speech is different than rehearsing what you're about to say. That activates parts of your brain required to actually move your tongue. Inner speech is just your basic, spontaneous thoughts and reading. That's it. All of these different voices in your head, however, contrast with outer speech, which is spoken or heard language, how I'm talking to you right now. That's out loud. There are too many little subtle and not so subtle differences between these 4 different types of speech to list, but there's one main similarity. They all use phonemes. Phonemes are individual speech sounds, almost like spoken versions of letters. The word ball, for example, has 3 phonemes, b, a, and o. My science fair project focused on these phonemes as a way to explore and further understand inner speech. Interestingly, we don't really know that much about how inner speech phonetics work in the mind. Luckily for me, though, we know how outer speech phonemes work. In fact, there's a part of the brain called the PSTG, or posterior superior temporal gyrus, a fancy way of saying the upper back part of the temporal lobe, located right about here, that we know, through multiple studies, plays an important role in outer speech phoneme identification. In fact, with detailed enough readings of brainwaves from that region, you can actually tell what phoneme someone is listening to. If you listen to ah, your PSTG brainwaves will advertise that to those who know how to read them. My aha moment came when I found that this exact part of the brain, the PSTG, is in fact active during inner speech too. From that point, my hypothesis basically wrote itself. Could it be possible to use the brainwaves of someone's PSTG to figure out what phoneme someone was thinking at a given time? Basically, could you phonetically read someone's mind? So, with the help of my mentor, I set up an experiment. I would show participants a video where they would watch and read silently in their head written representations of 3 phonemes, ah, o, and e, over and over while it recorded the brainwaves coming from the PSTG. Luckily for me, STEM, the school I go to, has an electroencephalogram, or EEG. It's a simple, non-invasive way to get the electric signals from the brain. I ended up having 7 participants wear the EEG while performing 100 repetitions of each phoneme for a total of 300 trials per participant, supervised, of course, by my mentor. The data were noisy and not of the highest quality, but it worked. Another stroke of luck? I got this process done just in time. Quarantine would begin less than a month later. At this point, I had my data. Brainwave readings from 1,500 trials across 5 participants. 2 of the files ended up corrupted. Unfortunately, the raw form of EEG data is practically illegible. It's called time series data. It's the straight-up electrical magnitude of a person's brainwaves from a certain area of the brain every 2/50th of a second. Trying to find anything interesting would be like having a tone-deaf person try to pick out every note in a Beethoven symphony. So I was gonna need to process it. Luckily, I had signed up for a UW in the high school course in the fall and was therefore able to access a bunch of data processing software for free. Mainly, MATLAB. MATLAB is a kind of even cooler version of Excel, but with lots of different plugins that can do very specific things. I used one such plugin, EEG Lab, to perform what's called a fast Fourier transform, converting time series data to time frequency data. It basically breaks apart every oscillation in a brainwave by frequency to give a graph that looks something like this. Following the symphony analogy, it would be like separating out the wall of sound by every note that was played. This part of the graph demonstrates how loud the highest notes are being played, this part of the graph demonstrates how loud the lowest notes are being played, and everything in between as well. In between. This is helpful because different brainwave actions happen at different frequencies. Some things happen at lower points in the graph and some things at higher points. One scientific article I had read suggested I look specifically at frequencies around 112 Hz, about here on this graph. There wasn't nearly enough time to look everywhere, so I focused on that section of the data. But that's not all. Remember how I said brainwaves were like a symphony? Yeah, well that implies that multiple instruments are playing similar notes. The time frequency chart shows all the instruments playing each note, and we want just the instrument, or part of the brain, that focuses on phonetics, remember? EEGs take readings from all over the brain, readings that bend and distort together coming through the skull. If you want the activity of a certain part of the brain, you have to look closer. So I created an equation to try to further reduce noise. Since I'm expecting brainwaves at around 112 Hz to change regularly every 0.5 seconds, that's how long my trials were, I made an equation which attempts to the best of my ability to get rid of anything happening at a slower rate than 0.5 seconds, trying to focus specifically on things caused by my trials. Apparently, this equation is very close to the standard low-pass filter equation, something that does exactly what I was trying to do, but I didn't know that existed till much later. I was just playing around with fake graphs on Desmos. The final step in noise removal, in some almost vain attempt to get rid of everything happening faster than the trials, I didn't really know how to do that mathematically, I finally decided to average my 300 trials per participant down to 30 trials, something that would greatly impact my statistical reliability. Though, Even with that accounted for, my results ended up significant. Now that I'd gotten rid of about 2/3 of the things that could skew my data downwards, I was able to finally test to see if brainwaves from this part of the head at 112 Hz could actually be used to determine what phoneme someone was thinking. I first had to summarize each trial into a single number. I used a linear regression slope to do that. Then I had to put it into a clustering equation that made a prediction as to which phoneme was thought during each interval based on the brainwaves alone. And success! At least 50.67% of the time. That might not seem like a lot, but remember I was working with 3 phonemes. If there was nothing there, we would expect to see something a lot closer to 33.33% accuracy. In fact, no matter how you measure the p-value, a measure of statistical significance, of these data, you get less than 0.05, a strong indicator that these data are in fact representative of a real phenomenon and not just random chance. That's right. All that fancy wording means that you can phonetically read someone's mind by reading brainwaves from their PSTG. Well, almost. Before I go into more detail about that almost, I should talk a bit about some of the inconsistencies seen in my data, because there are a few. First, if you break the accuracies apart by participant, you get something interesting. Some participants are much more accurate than average, while some are much less. Why would this participant have such a low accuracy? The answer, as my mentor and I both believe, lies in 2 factors: the phenomenon of cortical localization and the interesting quirk of EEG electrode placement. Basically, different parts of the brain process different things. Your sensory cortex processes your senses, and there are different parts of that cortex that process the touch from each of your fingers, for example. The same is true of phonemes. Different phonemes, as one article I read contended, are processed in different parts of the PSTG. And, since an EEG is positioned at a single point, the more equidistant the EEG's electrode is from each of the 3 points that process A, O, and E, the more similar the brainwaves produced when thinking those phonemes will appear, and the less accurate the results will be. Why would the EEG move between participants, you might ask? Well, everyone has a slightly different head shape, and therefore a slightly different brain shape. The EEG, however, cannot determine exactly what part of the brain, or even skull, it's placed on. So, basically, human error. This is further compounded by the fact that brainwaves are conducted wildly different through different parts of the skull. If you look at this graph here, the accuracies of different electrodes in one participant, you'll see that, though the electrode nearest the PSTG was most accurate, the electrodes on top of the head was also very accurate. This is likely because brainwaves from the auditory cortex, of which the PSTG is a part, are often conducted to the top of the head by the shape of the skull. You can even see that moving the electrode slightly down and to the right drastically decreases accuracy. So, if one participant's head is slightly different, they might have a massively less accurate reading. There's no other reasonable explanation, however, for accuracy. If moving the electrode means readings become more accurate, that means only that that part of the head conducts electricity best from wherever on the brain inner speech phonemes are processed. Since the highest accuracy is by the PSTG, that only further supports my hypothesis. If there are so many little things that can decrease accuracy, nothing that can increase accuracy besides actual accuracy, and under the most scrutinous p-value calculations, the data are still statistically significant, that pretty strongly suggests a real phenomenon. I also ended up writing a scientific article on this experiment for class, highly edited by my mentor. She agreed with all my conclusions. I know, that's kind of crazy. In fact, she's pretty certain true mind reading technology, like the actual ability to read minds, will be publicly available much sooner than anyone can imagine. So now back to that almost. My results, 50.67% accuracy for 3 phonemes, are great for showing that there is something tangible that can be further explored. However, there are about 44 phonemes in English. That would mean incredibly incoherent readings with this current technology. Even when accounting for the inaccuracy of the cheap EEG used for this experiment and the absence of actual aligning technology, this exact method is far from whatever the final process will eventually and inevitably run real-world mind-reading technology. But why exactly do we even need such an invention? Well,
The ability to phonetically monitor inner speech could change much of the way psychological disorders like depression, anxiety, body dysmorphia, and eating disorders are diagnosed and treated, as they're tied in many cases to one's internal description of themselves and their surroundings. Having a way to actually access those negative or destructive thoughts as they occur, to analyze them and understand them, could revolutionize our understanding of modern psychology. Ethically, we have to tread lightly. The ability to identify certain feelings from fMRI scans have already led to indictments of crime in India. Reading something as complex and personal as the verbal thoughts inside one's head could lead to controversy and violation of privacy, especially if used illegally or under totalitarian or oppressive governments. Russia, China, and America have a bad reputation of both misusing technology for power and not following international law. Of course, these concerns are still decades away, but they're important to address in any discussion of inner speech. I think ethics is a good place to end it, because this really is a story about a very human science. Not to plug linguistics, but it really is underrated. It's the perfect intersection of STEM and the humanities. It's also just really cool, and you can study it from your bedroom, though neuroscience is a different story. Another piece of advice, just email professors. They're usually helpful. In any case, I hope this inspires you to try to do something you don't think is possible, and looking a bit more into linguistics couldn't hurt either.
Thank you so much, Nathan, for that insightful and inspiring presentation. We truly enjoyed learning about both neuroscience and linguistics. The connection and your findings are truly fascinating. If you have any questions for Nathan or just want to reach out, be sure to reach out on his social media. Or you can also email us your questions at samamishtscn@outlook.com or DM us on our Instagram at samamishtscn, and we would be more than happy to connect with you. All of it, of course, will be linked down in the description. And thank you to everyone who joined us today. We truly hope that you enjoyed this talk, which is just one in a series of many this summer. And as this is a series, we have to shout out our next talk in this series, which is on Tuesday, August 18th at 4 p.m. PST. We have a talk from the amazing Amy Lau on what harms orcas and what you can do about it. So be sure to join that talk and the many more to come during the summer on Tuesdays at 4 p.m. You can also stay up to date with us on our Instagram and be sure to subscribe to our YouTube channel. Thank you all once again and stay safe.